We're going to use the binomial probability formula to answer a simple question. What is the probability of getting exactly 3 2s when we throw a first 6-sided die 7 times? First, let's identify the variables. We are throwing a die 7 times, so n, the number of trials, is 7. We want exactly 3 of those rolls to be a 2, so k, the number of successes, is 3. And because we are using a first 6-sided die, the probability of rolling a 2 on any individual throw is 1 out of 6. So p is 1/6. That also means that the probability of not rolling a 2 is 5/6. We can now put those values into the binomial probability formula. We have 7 choose 3 multiplied by 1/6 to the power of 3 multiplied by 5/6 to the power of 4. Let's build those 3 parts in Visuali. We'll start with 7 choose 3. Using the factorial definition, this is 7 factorial divided by 3 factorial multiplied by 7 minus 3 factorial. So at the top of the diagram, we have 3 branches calculating the factorial values. 7 factorial gives us 5040, 3 factorial gives us 6, and 7 minus 3, which is 4, so 4 factorial gives us 24. We multiply 6 by 24, giving us 144. Then we divide 1040 by 144. Then gives us 35. So this entire group of units represents the first part of the binomial formula, 7 choose 3 equals 35. Now let's look at the probability of the 3 successful outcomes. Remember that in this problem, a success simply means rolling a 2. The probability of rolling a 2 is 1/6. And we need exactly 3 of them. So the next branch calculates 1/6 raised to the power of 3. That gives us approximately 0.0046. Same calculation for the remaining 4 rows. If exactly 3 out of 7 rows are 2s, then the other 4 rows must not be 2s. 5 possible numbers on the die are not 2, so the probability of not rolling a 2 is 5/6. We therefore calculate 5/6 raised to the power of 4. That gives us approximately 0.482. Now the structure of the original binomial formula becomes much easier to see. We have 3 branches. The first branch gives us 35, representing the number of different ways in which 3 2s can occur among several rows. The second branch represents the probability of getting those 3 2s 1/6 cubed. And the third represents the probability that the remaining 4 rows are not 2s, 5/6 to the 4th power. Now all 3 branches can come together. We multiply 35 by 1/6 cubed and by 5/6 to the 4th power. The result is approximately 0.0781. In percentage terms, that's about 7.81% probability of getting exactly 3 2s when we throw a first pair die 7 times. If we look at the original binomial formula, all of this information is compressed into a single mathematical expression. Then we can follow those separate calculations through that diagram until they converge on the final probability.